Hey guys, and welcome back to another video. So this is the first video of the calculus series here on this channel. Okay, so this first video is going to dive into limits. Alright, so to begin with, let's just introduce what even is calculus. Okay, so calculus, the main idea behind all of calculus is the limit, right? So calculus, the main idea is limits. So essentially, a limit is like you're approaching something, and you're like getting infinitely close to something, but you're never really reaching that thing, right? So you can get like infinitesimally small and like infinitely close to like a point, but you're never actually reaching that point. So that's essentially what a limit is, and I'll make it more rigorous in a bit. But then from limits, we can branch off into the two most like important areas of calculus, which is derivatives and integrals. Derivatives, integrals, right? So briefly speaking, derivative is really just like an instantaneous rate of change, and then integral is like accumulation, right? It's like accumulation function of a sort. So you can like think about this like differentiation is essentially like you're taking like a large object, right? And then you're breaking it up into like smaller pieces, and you're looking at each individual piece, right? So that's essentially what differentiation is. Whereas integration is the exact opposite, right? You're taking a bunch of little pieces and you're putting them all together to get the whole bigger object. And so in this way, differentiation and integration are inverse operations. All right, cool. So that's like the brief introduction of what calculus really is. Because this is a new topic, because before calculus you've been learning like about algebra, precalculus, trigonometry, and those are all linked together. But then now you're getting to calculus, a completely different area of math. So it's important to have like a nice introduction of what we're really about to learn here. All right, cool. So now let's actually talk about what a limit is. So remember, limits are the backbone of calculus. So this is important to understand. So geometrically speaking, suppose we have some function like this, right? So some function, and then we have some point C, and then this will be f of C. So this is some function y equals f of x, right? All right, so the limit as x approaches C of f of x. So what does this mean? So basically, this is like the idea. Is like you're approaching C. Let's just say you're approaching C from the left-hand side, right? So as you approach C from the left-hand side, as x gets closer and closer to C, you're trying to see what value does the function approach. So what value does the graph approach? Well, as you get closer and closer to C, you can just trace the graph of this function, right? So like you're going like this, you're going up and you're going up, and then eventually you're approaching this point right here, which in this case is f of C, right? So in this specific scenario, the limit as x approaches C is f of C. Right? But note that we can actually not conclude this right away because of two reasons. First, we only determined x is equal to f of C when we approach C from the left-hand side. We also need to approach C from the right-hand side. So if we approach C from this side now, notice that we also do in fact get the same value. We get this point again. So in this case it works out, but that's not always the case, right? It need not approach f of C from the right-hand side. And secondly, the function might not even be defined at C. Like f of C might not even be defined. So for example, if here, instead of like being continuous, there was like a point discontinuity right there, right? Then the thing is, this is no longer f of C, right? Because f of C is not defined. So we'll just call this like some value L, right? So clearly, we know that f of C is not defined. So f of C is undefined because of the point discontinuity, right? However, the limit still exists, and this is very important, right? Because if you approach C from the left-hand side and the right-hand side, if you approach C from the left-hand side, you approach this point, which is not defined, but you do approach that point. And then from the right-hand side, again, you approach that point discontinuity. And so because you approach the same point from both sides, that is the value of the limit. So the limit as x approaches c of f of x for this example is equal to L. Even though L, like f of c, is undefined, the limit as x approaches c f of x is defined. So this is just like, that just goes to show that like the limit, or like the function need not be defined at c for the limit to exist at c. All right. So that's like a geometrical interpretation of what a limit is. So you're essentially getting arbitrarily close to some point c, and you're seeing what value does the function approach. All right, cool. So now let's just do some like basic examples of evaluating limits. All right, so starting off super simple, let's evaluate the limit as x approaches 1 of x squared, right? So let's just evaluate this graphically for now, because that's how I've taught you so far, or taught you. So if we just graph x squared, we get a parabola like this, right? And x squared is continuous everywhere, right? And I'm sure in previous math classes, you know what continuous means. You probably heard that it means that you can draw the curve without lifting up your pencil, right? So in calculus, that definition doesn't necessarily like slide. Like we need a little bit more rigorous definition for now. But for now, that definition is fine, right? Later on, like in a couple of videos, I will define rigorously what continuity actually means. But for now, we know from previous math classes that x squared is a continuous function. And so therefore, we can just simply evaluate this limit by substituting 1 into this function. So this is really just equal to 1 squared, which is 1. If x squared wasn't continuous at x equals 1 though, then this would not work. So let me show you an example of where that is the case. Okay, so I'm just going to keep this x equals x squared. All right, so let's do another example. So now let's evaluate the limit as x approaches 0 of 1 over, or let's evaluate the limit as x approaches c of f of x, where, and this is like evaluating limits graphically. So I'm going to give you this graph of f, right? All right, so this is the graph, right? So what's the limit as x approaches c of f of x? So this is the graph of y equals f of x. Okay, so what's the limit? Well, to do this, we have to consider when we approach c from the left-hand side and when we approach c from the right-hand side. So approaching c from the left-hand side, we notice that the function value gets closer and closer to L. It's not defined at c though, notice, because there's a point discontinuity, but it's getting closer and closer to L. So the left-hand side limit is equal to L. So now if you approach it from the right, we also notice that the function value is getting closer and closer to L. So therefore, the limit x approaches c of f of x is equal to L. All right, cool. So this is basically evaluating limits graphically. So there's also another way that we can evaluate limits. That is, we can evaluate limits if we're given a table. So for example, if we want to find the limit as x approaches 2 of f of x, right? And we're given the table, the following table. Okay, so suppose we have this table and we want to find the limit as x approaches to f of x. Well, notice that x is getting closer and closer to 2 from the left-hand side and from the right-hand side. So as x is getting closer and closer to 2 from the left-hand side, that is, it's going from 1.9, then 1.99, 1.999, 1.999, so on. The function values f of x is getting closer and closer to 5, we can see, because 4.9, 4.99, 4.999, 4.999, right? So it's getting closer and closer to 5 as we approach x from the, or as we approach 2 from the left. As we approach 2 from the right, we're also, so 2.1, 2.01, 2.001, approaching from the right, we're also getting closer and closer to 5, right? 5.1, 5.01, 5.001, and so on. So therefore, because as we approach 2 from the left and right, f of x is approaching 5 both cases, that means that the limit as x approaches 2 at f of x, this is equal to 5. Okay, so this is an example of evaluating a limit using a table. All right, cool. So now that we have that covered, let's talk about some limit properties, limit laws. All right. So we have our limit laws. So these are going to be very important for us throughout the rest of this course. All right. So we just have to assume, so if limit as x approaches c of f of x is equal to L, and limit as x approaches c of g of x equals m, then the following properties hold. So first, we have the limit as x approaches c of f of x plus or minus g of x. This is equal to L plus or minus m, respectively. All right, number 2, if we have the limit as x approaches c of some constant k times f of x, you're simply multiplying that same constant to the limit value. So this is just equal to KL. So for some real k. Okay. Number 3, the limit of the product. So limit as x approaches c of f of x times g of x. This is simply just equal to L times m. Number 4, the limit of the quotient. So limit as x approaches c of f of x over g of x is equal to L over m, given that m is not equal to 0. Okay. Number 5, we have the limit as x approaches n, or sorry, the limit as x approaches c of f of x to the n. This is just equal to L to the n. Okay? And this is for all rational n. So whenever n is a rational number, so that is, you can write it as like p over q, then this works. So yeah, these are all the limit laws. So we have the limit of a sum and difference. We have the limit of a constant multiple, limit of the product, limit of the quotient, and limit of a power. Okay? Yeah. All right. So now that we have these limit laws, we can get some practice using them. So I'll erase all these. All right. So example 3. So here I'm just gonna be like, so given limit as x approaches, let's say 3 of f of x is equal to 5, and limit x approaches 3 of g of x equals 7, evaluate the following. A. So we want to evaluate the limit as x approaches 3 of f of x plus g of x. Right? So we know from our limit properties that, from our limit laws, that this is just equal to whatever the limit for f of x was plus whatever the limit for g of x was. Right? So in this case, our L is equal to 5 and our M is equal to 7. So the limit of x approaches 3 of f of x plus g of x is equal to L plus M. So this is equal to 5 plus 7, which is just 12. Alright? Cool. Part B. Let's evaluate the limit as x approaches 3 of, let's see, f of x squared. So the limit as x approaches 3 of f of x is 5. So then if we square f of x, we simply just square 5. So this is just equal to 5 squared, which is 25. Alright? Alright. Now let's see, we want the limit as x approaches 3 of g of x over f of x. So this is where it gets important to note the order, right? So we want g of x over f of x, not f of x over g of x. So a lot of students might mess this question up and immediately think that they're asking for f of x over g of x, write 5 over 7 and move on to the next question, but they're going to be wrong because we want g of x over f of x. So this is actually equal to 7 over 5. Okay, so just be really careful when you're reading the question because you have to, the order might be different. All right, let's do one more. So let's say we want to find the limit of x approaches 3 of f of x times g of x. So notice that in multiplication, the order doesn't matter because multiplication is commutative, right? I feel like the only other place where the order does matter is in subtraction. So if you have f of x minus g of x, that's different from g of x minus f of x because subtraction is not commutative, and same goes with division. But everything else, the order doesn't really matter. But if we have this, so then we simply just multiply the corresponding limits. So this is just equal to 5 times 7, which is 35. All right, cool. So that's just like an example of how the limit laws apply. Okay? So now we're reaching the end of this video. There's a couple of last remarks that I need to make. So an important thing, so just like some notes, important notes. So firstly is that the function need not be defined at the point of at where the limit is approaching. And I've talked about this before also. So essentially what I'm trying to say is if we have the limit as x approaches c of f of x, then so for this to be defined, so for this to exist, f of x need not be defined at c. So f of c need not be defined. Right? But then that being said, what needs to be true is that the limit as x approaches c from the left-hand side, and so this is a new notation. So this with the c to the kind of negative exponent, all this simply means is that I'm interested in the limit as x is approaching c from the left-hand side, right? So negative means left-hand side, and then limit as x approaches c from the right-hand side is with a plus instead of a minus. So this is you're approaching c from the left, and then c to the plus, that's you're approaching c from the right, right? So in order for the limit as x approaches c to exist, all that means is that these two limits need to be equal to each other. So if this is equal to L, then this needs to equal L. And then the whole limit as x approaches c will also equal L in this case. But let's just say, for example, that the limit as x approaches c from the left-hand side is equal to m, then now all of a sudden this limit is x approaches c does not exist, right? So now this does not exist, and we just write DNE, right? So this means it does not exist. So yeah, but I'm just gonna go back to the previous solution. So, yeah. Okay. Cool. But other than that, I think that's it for this video. So I hope you guys enjoyed and you found this video helpful. If you did, please make sure to leave a like and don't forget to subscribe. The next video is going to be on the squeeze theorem. So stay tuned and I'll see you guys in the next video.